as Hans said, I'm here to tell you about what's available at I23, which is a microfocus beamline at diamond light source. So as a quick overview, I24 is a tunable microfocus beamline. We have energies from 7.8 to 25 keV currently. We have a relatively high flux density of about 3 × 10 to the 12 photons per second. And our beam size can go from 5 by 5 microns up to 50 by 50, depending on the size of your crystal and your needs. We also have a very adaptable sample environment, which includes a pin-based goniometer, a horizontal goniometer for trays, and then a separate setup that we can bring down for serial crystallography. So this is just a picture of the end station here. A laser pointer up, there we go. So we've got our 2 detectors, which I'll talk about a little bit later. This here is the actual end station where all of the actual X-ray diffraction experiments happen. And then we've got our robot and our sample viewer. It is an undulator beamline with a secondary source. That's part of how we managed to get our high flux density. And as I said, the sample environment is quite adaptable. So you can do a lot of different experiments at I24. That includes rotation data collection, your kind of standard bread and butter crystallography. We're optimized for both SAD and MAD phasing data collection. We have a fast grid scan option for if you've got either very small crystals that you can't find, or if you're collecting membrane proteins in lipidic cubic phase, which you can't visualize. As I mentioned, we have the in situ plate data collection available if your samples don't like being cryoed, for example. We have our serial data collection setup, which is now becoming more standard, but still requires a bit of beamline staff intervention. And then finally, we have our time-resolved experiments, which again are still in development, and most of these involve a fair amount of intervention by the beamline staff to get done, especially in current COVID times where you guys aren't actually allowed to come to the beamline. So I'll start with the one that you're probably most familiar with, the pin mode. So here is our vertical goniometer holding a pin. We have our cryostream, apertures and beam stop. This here is the top of the robot, which picks up your sample and puts it in the cryo. So I think we can hold about 37 pucks. So we're a very high capacity beamline, which has been very helpful considering we're doing all of the sort of loading for the week, preferably only once, instead of having to drive to site multiple times. So along with the standard rotation, you can also, if you do multiple collections on, say, the same protein and you want to combine your data sets, we have a multiplex data processing option, which will, as you collect more and more data, will combine it and eventually spit out an MTZ at the end for you. We have helical scans if your protein is particularly radiation sensitive and you want to be constantly exposing new areas of it. As I mentioned, we have the fast grid scans for small crystals or for locating them. You can also use the grid scans to do X-ray centering if you want to do that. We have a fluorescence scan option, which is mostly used for the SAD and MAD phasing to first define if you actually have the element you're looking for in your crystal to do your phasing. And I've already touched on the high capacity robot. So, as I mentioned already, we have a number of auto processing pipelines available at Diamond. So for the most part, if you've collected a complete data set in one sweep, a whole plethora of pipelines are kicked off, and hopefully within sort of 10-20 minutes, you actually will have some pretty well processed data. I know there are quite a lot of people that will just take the autoprocessed and go straight into molecular replacement and refinement straight after. So yeah, that's a big time saver. It also means you can actually check almost straight away, especially with like fast DP, if you've actually collected enough data on that one crystal to have a complete data set. So this is an example of the grid scan options that we have. So this one at the top is just of a very large lysozyme crystal, which I've done a grid scan across the whole crystal, and it's given me a sort of heat map for what is the best diffracting area of the crystal. So this is also particularly useful, like I mentioned, for membrane protein in lipidic cubic phase, where you can't actually find the crystal by eye after it's been cryocooled. And this here is an example of a mesh which we've just scooped through a load of microcrystals and then collected a grid scan on it. And again, you get this, this heat map, which tells you sort of the best diffracting crystals. And you can click on these individual boxes and it will bring up this picture of the diffraction that you're looking at. Onto the tray mode. So we have been using the tray. The problem with the tray mode, I guess, is the fact that it has to be hand mounted. There's no current robot loading of the trays. So we haven't really been using it much for users lately, but we have been using it in collaboration with XChem to do some room temperature drug discovery experiments for COVID-19 on the MPro main protease. So with the tray mode, you can collect sort of plus or minus 10-degree rotation of the tray. Any more rotation and you run the risk of actually colliding the tray with something. So you're actually limited to only doing a maximum of plus minus 10 degrees rotation. In our hands, at least with the MPro crystals, it would take about an hour to collect a full data set of these 20-degree wedges. And these were all fed into the multiplex pipeline, which made processing a lot easier. And this here is just an example of one of the ligand hits that we managed to get with the MPro proteins and one of the ligands from XChem. And here's just an example of the sort of output you can expect from multiplex. So this will either combine small wedges for you into a complete data set, or it can also combine very large wedges or complete data sets if, say, you're looking to do some sort of anomalous phasing to get the redundancy up. It will also look at all of your data sets in context with each other and remove any outliers which are actually making your data worse. So say you've got 10 data sets and one of them was sort of half an angstrom worse resolution and it's actually just bringing down the quality overall. You can quite easily remove that so you can get the best data possible, as we show in this, this graph here, where the red line is all of the data and then the blue line is the after the outliers have been removed. We can see a fairly good improvement in the CC half. So yeah, this is also very useful for radiation sensitive samples where you're only able to collect a very short wedge before your protein dies. So yeah, very useful. The next mode is probably the more unique and interesting aspect of I24 which we're developing, which is the serial mode. So instead of collecting a rotation wedge of data, we collect a large amount of stills. And our preferred way of doing that at the moment is using this fixed target method. So we use these silicon chips, which have about 25,600 apertures in. And what we do is we take our chip and we put it onto a little stage with a vacuum attached to it. And then we just pipette a microcrystal slurry on top of it. This then has a vacuum applied to it. And what we hope as the result is that your crystals are pulled into the small apertures and held there in random orientations. And then what we do is we take the chips and we put them in these custom designed chip holders, and we seal them with a thin film of mylar, and that keeps them airtight and stops them from drying out, like so. We then take these chips and we put them onto these XYZ stages. And what it will do is it will raster through the individual apertures, and you'll get sort of a collection of stills data. So there is actually a paper summarizing this technique coming out hopefully very soon. It's just gone through the final reviewer and editor checks. So hopefully they'll be releasing this soon. It is going to come eventually with a video protocol, as it is from Jove, but COVID restrictions have prevented us from actually being able to film that video yet. But hopefully soon it will have all of the details you need for running your own serial experiment. We're also quite aware that a major drawback of this serial approach is the large amount of protein crystals that it actually requires. So we're typically pipetting about 200 microliters of protein sample onto our chips, which in an ideal world has about 10 to the power of 8 crystals in it. And obviously a lot of challenging samples it's going to be hard to produce this number of crystals. So we are looking at different methods of getting the crystals onto these chips. And one of these is this polypico droplet injector system, which uses an acoustic wave to fire very small drops of liquid onto the chip. So this has been developed mostly by Pierre Allaire at the XFEL Hub. And we have done some tests with sort of different crystal concentrations, loading them onto the chips, and it seems to work pretty well. And instead of using 200 microliters of crystals, this uses about, well, hopefully in an ideal world, tens of microliters instead of hundreds of microliters. The other option for serial that we have available at I24 is the extruder. So this requires your sample to be sort of in LCP or some sort of other viscous media. And much like at the XFEL, this will just be extruded as like sort of kind of like a toothpaste, and it will kind of go into the beam and will collect the fraction out of it. Again, this can also be a problem for sample consumption, but most serial techniques are, unfortunately, so it's just something we have to deal with. So the major problem, or one of the major problems still with serial data processing, is it's much more difficult than your standard rotation sweep, because all of the stills that you collect are in effectively random orientations, and we need to figure out a way to combine all of those random orientations into a complete data set. So we've been working on, again, some processing pipelines. This has been mostly in collaboration with the Dials team, particularly Nick Devenish. So he's been writing software for us to, mostly the current thing is to have a good idea almost immediately if your hit rate is high enough. So typically we want a hit rate of around 20 or 30% from a chip, and then that will hopefully get us a complete data set. But obviously this is very computationally expensive. So the quicker we can know if we've collected enough data and can move on to the next sample, the better. So yeah, these processing pipelines are all in motion currently and kind of being developed as we go. And obviously the main reason for actually bothering with all this extra effort for serial crystallography is so that we can more effectively do sort of time-resolved dynamic experiments. So we now have a portable laser system. I say it's portable, but it actually involves using one of the diamond cranes to bring the large laser table into the I24 hutch. But we can now do sort of a laser activation experiment relatively routinely. So we just have the laser coming from the optics hatch, and it comes along here, and we focus it onto the sample position using these mirrors and this little optical prism just in front of the sample. So we get almost on-axis activation with the laser, and then we can probe with the X-rays. This is just an example of a photo cage we've used on some heme proteins. So when this cage is hit by the laser light, it chops off this NO molecule, and then we can see it binding the active site of this heme group here. We can also do slightly more complicated laser illuminations. So this was in collaboration with the Van Thor group at Imperial College London. And what they wanted to do was to take the ground state ligand conformation, activate it with a certain wavelength of light into a different state, and then they wanted to reverse it with a second laser pulse and watch the process of it flipping back. So this is probably one of the more complicated laser experiments we can do. So it obviously needs a lot of hands-on help from the Beamline staff to do it. But if you are interested or have a system where you want to do a laser experiment like this, we are very open to collaborations to sort of further refine the system. The other option we're working on currently, so most proteins aren't light activated, and making photo cages is very difficult. So we want to get this rapid mixing set up off the ground, where you load your crystals onto the chip, and then you actually just fire your ligand onto the chip, and then collect some data from it at a defined time point to watch the reaction happening. So this actually, these pictures are just from last week. So we're hoping to make some more progress on this in the next couple of months. The setup has already been used at T-Rex in Hamburg at Petra 3. So we're just kind of recreating what they've already done. So yeah, hopefully that will be available to the wider user community soon. And here's just a really terrible picture of the drops actually hitting the chips. The other new development that we have I24 is the cadmium telluride detector. So this is this top detector here. So instead of the typical silicon sensor on the Dectris, on the Pilatus detector, this is a new Eiger detector with cadmium telluride sensor. And this allows us to collect data at much higher wavelengths. So heading towards the range of 25 keV. So our initial tests have shown sort of a 22 keV is a fairly good compromise between data quality and absorption. But the main draw of this is the fact that using higher energy X-rays, we can actually collect more data per unit dose. And this is in part due to decreased absorption in the sample from the beam. And also if your crystal is small enough, the photoelectron escape of the X-rays. So instead of the electrons moving within your crystal and hitting something and damaging it, if your crystal is small enough, the electron will actually fly out of the crystal and not cause damage to it. And then there's also an increase in the elastic scattering with the higher energy. So there's been a couple of papers on this already, as far back as 1984, talking about the theory of it by Arndt. But we are also working on releasing a paper on this. This work was done by Selena Storm, and the paper is currently in preparation. But what we have found is that the improvement in the intensity that we're recording of our diffraction spots is about 3.5 times improved on your standard lower energy data collections. So we're heading towards the end of my talk now, actually. So that leads me to talk about the future of I24. So we've recently secured not exactly a grant, I guess, approval to upgrade I24 along with the Diamond 2 upgrade. So Diamond 2 is obviously going to bring an increase in flux. And this is good for I24 because it means we can more effectively study membrane proteins, which need a higher flux to get sort of good diffraction out of them. So that will aid our efforts in drug discovery. Increased flux is also going to help with any microcrystal-based work we're doing, because you have such few unit cells that a higher flux means you can actually get more out of your small crystals. And it also means an improvement to the high energy data collection, because currently as we go to higher energies, we are seeing a reduction in flux. But the main future for I24 is going to be in dynamic room temperature crystallography. So we're currently working in sort of the millisecond domain. And upon the upgrades to the ring itself and the upgrades to I24, we hope to be able to actually access the microsecond domain. We're also hoping to incorporate an on-axis laser instead of having to go through all of these twists and turns with the mirror to get the laser into the sample. And to keep track of these dynamic reactions and also add an extra layer of validation, we're also hoping to incorporate various types of spectroscopy, including X-ray emission spectroscopy and X-ray fluorescence, and potentially UV-vis spectroscopy if we can figure out a way to fit it in. So on the left here is the current I24 setup. The horizontal goniometer for the trays has been removed here. And that is also the plan for the future to remove, because hopefully VMX-I will be up and running for users, and we won't actually need to do any more tray data collections. And then we're also going to, like I said, incorporate the X-ray fluorescence and X-ray emission spectroscopy. So that's here in green and blue. And then we also hope to incorporate a tape drive for another option for serial data collection. So obviously this has been a large team effort, and I've actually only been here for about 3 months as a Beamline scientist and a year before that as a postdoc. So a lot of this work has been done by Robin, Danny, and Selena, as well as John. Selena and John have since moved on to EMBL and PSI. We do a lot of collaboration with the XFEL hub, especially on the dynamics side. The dials team, who have been doing all of the help towards making serial data processing a lot simpler. Obviously, we wouldn't be very far without the engineering team who help us build all of the stuff that we want to use. And then all of our collaborators who have provided crystals or advice or helped develop tech along with us. So the Huff group in Essex, the Choose group in Southampton, Van Thor group in Imperial College, the Pearson group in University of Hamburg, and the Miller group at the Max Planck Institute in Hamburg. So the last thing is how to actually apply for some time. So currently you need to apply through the user administration system. So that's direct to Diamond for beam time. And then you can also apply through the iNEXT, which is pretty much copying and pasting what you've written in the UAS into the iNEXT. Yeah, it's hoped that soon this will be just a single process instead of 2. The next call actually ends on the 3rd of March. So if you are looking for time, please do submit your application soon. If you can't meet the 3rd of March deadline, there is also rapid access plans available if you sort of a month or 2 down the line find you suddenly have lots of crystals and need some time. So yeah, so that's everything from me.